company Drought Analytics, a spin-off of Forschungszentrum Jülich. Drought Analytics offers multi-day and seasonal drought stress and risk forecasts for the agricultural sector. And his talk will be about an efficient surrogate model developed in cooperation with Helmholtz-Zentrum.
All right. Thank you for this nice introduction and also the opportunity to present this topic and also our model HydracastAI. It's always bad to start with talking about droughts when it's raining, but I guess you all have in mind the last 8 weeks of really dry weather, and I think it's one of the driest springs since weather recording. So we actually can see that climate change is changing the precipitation patterns, leading to more severe and more frequent droughts, which is actually putting agriculture under a lot of pressure. So to cope this situation, it gets increasingly important to know the current and also the future state of the available water resources to make timely and good agricultural decisions, for example, regarding the selection of drought-resilient crop varieties, of irrigation logistics, or also on drought insurances. And while looking at meteorological forecasts, you have an idea about the rain that really reaches the soil. What really is important is the rain that infiltrates into the soil, the soil moisture, soil moisture that is available for the plants. So in this regard, I give a little example here so you can imagine this. On the right side, you see a sandy loam soil and the numbers of water stress a crop has on sandy loam soils in the past years and on loamy sand soils. And as you can see on loamy sand soils, the crops are experiencing 4 times more days of drought stress. So having this change of mind from meteorological to hydrological forecasts is really important. In this regard, my colleague Belleflamme² put on a hydrological model using PowerFlow and CLM, which is a physical numerical based model simulating the water cycle for the whole of Germany with a resolution of 600 meters and a depth of up to 60 meters. And then by forcing it with daily and seasonal weather predictions from ECMWF, we really can now give hydrological risk assessment, drought risk assessment, also using multi-member ensemble forecasts. The downside from it, it's highly computational intense. It takes a lot of time, so the seasonal forecasts are only available at the mid of the month, so they are not really working out. And to cope this and to get kind of an operational service, we need to speed this up. And this was the idea of HydracastAI, to really replace the current PowerFlow CLM model to provide time and cost efficient drought forecasting and risk analysis as part of an operational and scalable service. The HydracastAI is also predicting the pressure states. So from this, we are really flexible in the way we run the diagnostics and derive quantities out of it. So we can then predict the water table depth, the volumetric soil moisture, or the plant available water. The model is based on the forced spatio-temporal recurrent neural network developed by Andrew Bennett from Princeton, which builds on the predictive recurrent neural network used for video predictions, but with an initialized memory and cell states. So the architecture is shown here. We're using the different pressure values as initial states from our PowerFlow model, and the hydrological soil parameters like permeability and porosity to initialize the memory and cell states. The different depth layer, so we have 15 in total, are casted as individual channels to really reflect the heterogeneity of the subsurface. Then there's an action cell that allows that the external forcings, so our weather forcings, are really impacting and influencing the prediction, which is then kind of auto-regressive, predicting the next day, the next target, updating the memory and the cell state, and also using then the predicton as the new initial state for the next time step. So the data we used, as I already said, the initial pressure, we're using path flow and pressure outputs also for the targets. It's the same. As static parameters, we started with the main hydraulic characteristic parameters, so porosity, permeability, van Genuchten parameters, topographic wetness index. And as forcing, we first now concentrated on the meteorological forcings using the HARES data from ECMWF. Here on a daily time steps, so daily accumulated precipitation values, minimum and maximum temperature values, and also snow melt. The training was done for the time of 2011 to 2013, validated on 2014 and tested on 2015 and 16. The data pipeline was set up that it allows the stream of 4D hypercubes, which is basically just the subsections of the model domain with the flexible extent on the time and spatial dimension, and it allows us to iterate over the data set, having random access and also training on multiple GPUs. The training itself took place in 3 phases with increased rollout horizons. So with the first rollout horizon of 2 days forecast, then 35 days forecast, and then 120 days forecast. And to kind of balance the memory load, the patch size needed to be decreased with further rollout horizons. One training phase took around 24 hours on 1 joules booster node with 4 A100 GPUs. Then, of course, there's also an early stopping to monitor the validation loft, to not overfit the model. Also get a spatial, or implemented a spatial gradient penalty to get like spatial consistent pressure fields in the end. So to give some initial results, we can have a look at the water table depth. So we have a forecast for the 8th of May 2015 and then 30 days ahead. So on the right side you see the original data, on the left side you see our data from HydracastAI, and they are quite matching, which is already a good sign. We can, if we look at the change or the difference, we see that the Alpine region is not well reflected, which is also quite a challenging hydrological regime, and is also not that good represented in the original model. If we see how the error propagates throughout the rollout horizons, we see it starts with like 5 centimeters RMSE to around 30 to 35 centimeters. We have to check if this can be kind of coped or improved if we mask out the Alpine region, because for us, for agricultural kind of analysis, this region is not that critical. Looking at the plant available water, we see that the plant available water for the deeper soil layers, so in the upper part for the 2 meters, is matched really well. You see also this kind of Alpine region here, but looking at the total RMSE, you see it starts from 0.1% up to 4% RMSE in plant available water, which is really good, and we can already work with this. For the upper soil layers here at 50 centimeters, we see that it's not that well represented. Looking at the total RMSE here on the right plot, you see it starts basically from 10% to 30%, and this means if your plant is healthy or is already dead, so we have to work on this one. Nevertheless, this is also the horizon which is mostly affected by weather forecasting and also on the interaction with the plants, which this information is not yet included into the model. So we have to look at this. Nevertheless, we did a preliminary HydracastAI seasonal forecast for June. So we can see we have some quite dry soils in the east of Germany and in the south of Germany, both in the 50 centimeter horizon and 2 meter horizons. And next week there will be kind of a hot phase, so really affecting the upper soil, while there will be a little relief by the end of the month, especially like for the east of the domain and the center of the domain. And what you can also see is that this kind of dry conditions will not so much impact also the deepest soil layers, which is quite nice to see. Anyhow, this is just like one member, so this is not a risk assessment. We have to run it 50 times to really see, okay, what is the probability of these scenarios. So to give a conclusion and the outlook, HydracastAI did promise or did fulfill its promise. It speeds up the prediction by a factor of up to 2,500. So the 6-month forecast takes only 10 minutes now on a NVIDIA A100 instead of 411 node hours, which is way faster and cheaper, and we can really serve, or we can put it as an operational service. Then it also skillfully predicts the water table depth and the plant available water for the deeper soil layers, so we are quite confident with this. For the shallow soil horizons, we have to improve it, because this is basically for agricultural the horizon where which is most important. So we already improving the training, including information about the land cover and the crop types, and also extend the meteorological forcings. Then we also want to expand the training to the years 2018 and 2022 to have like drought periods, really, drought extremes trained, and then maybe enlarge the attention span and adaptive validation to really reflect the hydrological conditions in the upper soil layers. And with this, I want to thank you for your for this presentation.
Thank you, David. Any immediate questions from the audience? So I have a question. Are you in principle, or will you in principle be able to roll this out over the whole of Europe, given the models and the databases?
Right, currently we are having Central Europe because we have Germany and the contributing catchment areas, but the underlying data for the parameterization of the model is global data. So in theory, we can make up a model for the whole world. But of course, then you have to see like how good the data is if you have like global data. Yeah.
And you are still relying. Oh, there's a question, Peter.
Hi, I'm Peter again. So I'm just wondering, so I'm imagining the situation that you roll this out and that like a farmer or some official or so sees these predictions. How do you deal with uncertainties and communicating them?
Yeah.
Especially when you're, if I understood you correctly, you want to go for extreme cases, of course, because that's the most important, I would guess. How would you communicate them? Is that just yet another color map?
No, this is actually a really hard topic, how to communicate these uncertainties. So one thing is, based on these 50 ensemble member forecasts, we can say, okay, what is kind of the risk of going into extreme areas of, for example, plant available waters. So this is something we are currently also working together with farmers and also with other stakeholders from industry, that this information really, or that the people and decision maker can really work with this probabilities or with this risk. Like with the with flooding, we have this kind of risk awareness that's saying, okay, there's a risk that something's going on, and then these steps are taken. And for drought, it's a different different topic, and we need to develop this. But we already have seen that basically the forecasted, also the 50-member ensemble forecasted, are better than just using the probability based on the time series from the past years. So we already have an improved risk assessment through the forecast.
Thanks so much.
Thank you.
All right, then let's thank David again